last thing from 5.3 is applications of exponential function. And this is still going to be the natural number. This is the natural number a naught e raised to the k times t. Or negative if it's a declining case. Plus or minus. Alright, so where we have to actually find the equation, which they should give us all the information we need. First example, population of Arizona was 6.6 million in 2010. Alright, so 2010 will be times 0. So 2010 is times 0. That means the time are the number of years after 2010. Our initial population was 6.6, and I'm just going to leave it in millions. That's our A naught. And then they gave us this, all right? The population was growing exponentially, continuously, at a rate of, and so it was growing by 1.44%, right? That's how that would be the, so it's kind of like the interest rate problem. That's the K. That means K is point, it's growing, so it's positive, 0, 1, 4, 4. That's what K is. Alright, and then my equation is A equals 6.6 e to the 0.0144 times time, keeping in mind it's in millions. Alright, assume the trend continues, estimate the population in 2016. Alright, so 2016, that would be 6 years after our start, 2010. And so I would plug t equals 6 into this equation, so a equals 6.6 e to the 0.0144 raised to the 6th. And get my approximate, so 7.1955, so I'm going to round that to 7.2. Remember, million people. Alright, 7.2 million people by 2016 about. Alright, the last one. The intensity of the sunlight on the surface of a lake is 300 watts per square meter. For each foot increase in depth in the lake, the intensity of the sunlight decreases by 10.5% per foot. So every foot you go down in the water, you feel the sun less, right? And again, eventually there's a point where you don't hardly feel it at all. Alright, find the equation that represents the intensity of the sunlight at any depth, and then use it to find the intensity of the sunlight at a depth of 50. Alright, so I'm going to let I be my intensity, I naught, e raised to the, since it's not a time, I'm going to use k times d. Alright, I is going to be my intensity, d is my depth. In feet. Intensity is in watts per square meter, watts per meter squared. Alright, my initial on the surface, the surface would mean we haven't gone in, that would be depth of 0, right? At the surface. Alright, K, well that's what this is, right? The intensity decreases, so I know it's going to be negative when I plug it in. Negative 0.105. Alright, and then we want to find, so my equation, my intensity equals 300 e to the negative 0.05 times d, my depth. And then, so there's the first part. There's the equation that represents the intensity of the sunlight at any depth. Use it to find the intensity of the sunlight at depth 50 feet, so my depth is 50. I'm going to plug it into that equation. And really the biggest thing here is just make sure you're careful when you plug it in. And so it comes out, not a whole lot of intensity, 1.5. So basically, it's very dark. So I'm just going to round 1.6 watts per meter squared. You can't see very far. It's very dark at that point. And it should make sense. It's pretty far. Right? 50 feet is pretty far down into the pond. It should make sense. The intensity is very slim at that point. Right? Probably couldn't be able to see it all. We'll stop there. All right, so that was a review of exponential functions, base E, and some simple applications. We'll get into more complex applications later in the chapter.